Here's a more complex example. Perhaps it's taken from a first-order problem, which is an inductor. And the question says, find the time constant of the circuit. In order to do that, you'd need to find the resistance that the inductor sees. So you look outside the inductor, and you see the circuit involving 3 resistors, a dependent source, and that does not look like a single resistance. But you know that a circuit that has only dependent sources, like this one, can in fact be simplified down to a single resistor. In order to do that, you've got to use method 4, the method of test sources. So the first step in this is to redraw your circuit, the part that you want to find the Thevenin equivalent of, so that would be without the inductor, and redraw it alone. Next, add your test source. Your test source can be a voltage source, or it could be a current source, whichever makes the problem easiest. Let's firstly try a voltage source. If you tried a voltage source, you'd need then to determine how much current flows through is caused by your test voltage source. So here's your VT of 1 volt, and here's your IT that you got to measure. Now this is going to be difficult because what we'd really like to know is what V sub x is. If we know what V sub x is, our dependent source would look like a independent source. We would know what that voltage is anyway, and we could solve for the rest of the circuit. A voltage source won't give that to us. So instead of using a voltage source, let's see what happens if we put in a current source. So now we're using a 1 amp I test. We still need to find both IT and VT, but now our IT is constrained to be 1 amp. We just need to find our VT. And now that we've got a 1 amp current source, now all of a sudden we know that if there's 1 amp flowing through this 3 ohm, then Vx has to be equal to 3 volts, just by Ohm's law. And that means that this dependent source has to be equal to 6 volts. And now we can go, that goes a long way towards finding VT. We can either use mesh or nodal, or if we could collapse resistors. I don't see any resistors that collapse here. So let's use nodal. That would be my preferred way to find a voltage, just like mesh would be my preferred way to find a current, since nodals find voltages and meshes find currents. If we have our ground down here, then that means this node here has to be 6 volts. And if this node is VT, and the right side is 3 volts less than the left, then this must be VT minus 3 volts. And armed with that work, we can begin writing our nodal equations. So let's begin by writing the nodal equation for that node. The current flowing to the left out of the 3, we can say is equal to VT minus 3, that's the current on the right of the resistor, minus the current on the left of the resistor, divided by that resistor value. And that should look kind of suspicious that it's -1, and that shouldn't surprise you because that's the voltage going to the left out of the resistor. But you could also have just seen it's -1 by saying there's 1 amp guaranteed to go into it from our test source. So let's just write that as -1. That's the current going to the left. The current going down would be equal to the voltage on top of the resistor minus the voltage on the bottom of the resistor divided by the resistor value, and then plus the current going down through the 5 ohm resistor. So that would be VT minus 3 over 5, and all that is 0. So simplifying that a little bit, we're going to move our constants to the right, and we get VT minus 9 plus VT over 5 equals 3/5 on the right plus 1. And now we've got all the parts on the correct sides. Oh no, we've got this VT minus 9 still. We've got to get the variables on our left. So that gives us, we've got 6/5 VT on the left, 1 plus 1/5. And then on the right, we've got 3/5 plus 10. So that's 10 and 3/5, which is the same thing as 53 over 5. So multiplying left and right sides by 5, we get 6 VT equals 53, or VT is equal to 53 over 6 volts. So armed with that, we know that the equivalent resistance is equal to, by Ohm's law, VT over IT. And our VT is 53 over 6, and our IT is 1, so our REQ is 53 over 6. And that means that our circuit, as seen from the perspective of our 2 Henry inductor, just simply looks like 153 over 6 ohm resistor. Maybe this example best illustrates the power of using Norton and Thevenin transforms within the context of a larger problem to solve. Now it's pretty clear to find what the tau is of this first order circuit, which is L over R, which would be 2 times 6 over 53 seconds.